Thank you, Mr. Chairman. Ladies and gentlemen, good morning. My name is Sabrina Vantadori, and the paper that I'd like to present you today is entitled Influence of Power Spectral Density Shape on Fatigue Damage. The goal of the present paper is the fatigue damage estimation in metallic structures under a biaxial random stress state, numerically simulated by varying the shape of the power spectral density matrix components. More precisely, my presentation consists of the following sections: introduction of the procedures usually employed in the fatigue assessment of metallic structures subjected to multi-axial random loading, presentation of the theoretical framework of the spectral criterion proposed by Carpentier et al., presentation of the numerical simulations performed by varying the power spectral density matrix components shape, evaluation of the effect of such shapes on fatigue damage, and finally conclusions. The procedure usually employed in the fatigue assessment of metallic structures under multi-axial random loading can be formulated in time domain or alternately in frequency domain. Time domain procedures are based on cycle counting methods and damage accumulation rules and require the knowledge of the time histories of the local stress-strain tensor components. Note that many records are needed in order to obtain reliable parameters of the loading process. Frequency domain procedure instead require no cycle counting methods. They need damage accumulation rule, and starting from the power spectral density matrix of the local stress-strain tensor components, an evaluation of the fatigue damage can be directly obtained. The criterion here employed to estimate the fatigue damage proposed by Carpentier et al. Is formulated in frequency domain and is a stress-based critical plane criterion consisting of the following three steps: definition of the critical plane, power spectral density function evaluation of an equivalent stress, and finally estimation of fatigue damage. In order to determine the orientation of the critical plane, let us consider a material point P in the structural components subjected to a general multi-axial random loading. The stress tensor at point P with respect to the fixed frame XYZ is that here reported, and by assuming that the random features can be described by a six-dimensional ergodic stationary Gaussian stochastic process with zero mean value, the power spectral density matrix at point P is that here shown, where the coefficients are defined by means the auto and cross correlation functions of the stress tensor components, where omega is the pulsation, lowercase t is the time, and capital T is the observation period. Now, let us consider a rotated frame, x prime, y prime, z prime, defined by the three Euler angles. The power spectral density matrix at point P with respect to such a frame can be computed by using the rotation matrix C, here reported at the bottom, where C stands for cosine function, S stands for sine function, and each subscript represent one of the three Euler angles. The rotated frame x prime, y prime, z prime is assumed to be linked to the principal stress directions at point P. Being such directions time varying during under random loading, we propose to define the following average principal stress directions. And more precisely, phi and theta is made to vary so that the direction z prime will experience the maximum of s free prime in a statistical sense, where such a condition is here shown, and where lambda 0 is the spectral moment of order 0 of the power spectral density function as free prime, mi 0 plus is the expected rate of mean 0 crossings of the stress S3 prime, and lambda 2 is the spectral moment of order 2 of the function S3 prime, 3 prime. The angle psi is made to vary in order to maximize the variance of the stress S4 prime. Note that the directions Z prime, Y prime are regarded as the average principal stress directions, 1 with cap, 3 with cap, and consequently the direction X prime is regarded as the average principal stress direction 2 with cap. The normal W to the critical plane is defined by the off-angle delta, being delta a clockwise rotation about the axis 2 with cap, and it is a function of the reverse, of the fully reverse shear and normal stress fatigue limits. Note that such a procedure agrees with the concept adopted in the original version of the criterion proposed by Carpentier et al. For cyclic loading. Now let us consider a new frame, PUVW attached to the critical plane. The power spectral, the stress tensor at point P with respect to such a frame is that he reported at the top, and the power spectral density matrix at point P can be computed by using the rotation matrix C tilde he reported at the bottom, where delta defines the normal to the critical plane, and gamma, and consequently the direction U, is made to vary in order to maximize the variance of the stress S4 seconds. The v-axis is finally the v-axis is normal to use so that U, V, W for a right and orthogonal frame. Now, in order to reduce the multi-axis stress state to an equivalent one, we propose to compute the power spectral density function related to an equivalent stress connected to the critical plane by means of the linear combination of the power spectral density functions here shown. Then the fatigue damage estimation is performed. Such an estimation depends on the algorithm used to count the loading cycles. The expected fatigue damage per unit time can be computed by using the formulation proposed by Dirichlet and here shown, where K and C are the parameters of the material normal stress SN curve, μ P is the number of peaks per unit time of the equivalent stress SEQ, gamma is the gamma function, and D1, D2, D3, Q, and R are fitting parameters depending on the first 4 spectral moments of the power spectral density function SEQ. A wide group of combined bending and torsion input signals is analyzed by varying the shape of the power spectral density matrix components. Under a biaxial stress state, the power spectral density matrix is that you show where the coefficients on the principal diagonal are spectral density, are autospectral density functions and are real functions, whereas the other components are cross-spectral density functions and are called complex functions. In the present numerical simulation, we assume that S1 and the stress S1 and S6 are in phase, so also the cross-spectral density functions are complex functions, and the power spectral density matrix is a symmetric matrix. 3 different shapes are analyzed for the spectrum S11 and S66 as shown more precisely. A triangular shape named spectrum of type 1, another triangular shape named spectrum of type 2, and a rectangular shape named spectrum of type 3. Independent of the shape, such spectra are characterized by the same input energy, the energy being proportional to the area under each power spectral density function. The median pulsation of the spectrum S11, named omega M11, is assumed to be fixed, Whereas the median position of the spectrum S66 is a name omega M66 is made to vary so that the different values of the position ratio are analyzed. Now let us consider, for example, the spectrum of type 1 by shifting omega M66 from left to right. 3 different types of input signals are generated, and more precisely, input signals totally uncorrelated, input signal partially correlated, and input signal fully correlated. The values of S11 are assumed to be fixed, whereas the values of S66 are computed so that the ratio between the variance of the stress S6 over the variance of the stress S1 is a constant and equal to 1. That is to say, the area under S66 is equal to the area under S11. The values of S16 and consequently S61 depend on the relative position of S11 and S66, and more precisely, S16 is different from 0 when S11 and S66 overlap, and 0 as well. The values of S16 are calculated by introducing the parameters, a parameter named coherence, which expression is shown at the bottom. And more precisely, S16 is equal to 0 for input signals totally uncorrelated for definition. For the present numerical simulation and partially correlated input signals, S16 is assumed to be equal to 0.1. Whereas for fully correlated input signals, S16 is equal to 1 for definition. The damage estimation is is performed for the above input signals by using the spectral criteria proposed by Carpenter et al. For proportional signals and for non-proportional signals. In the case of fully correlated signal, the expected fatigue damage for unit time is here shown against the position ratio. It can be observed that for fully correlated signals, the greater damage is that for the spectrum of type 2, which is only 1.1 times greater than the damage for the spectrum of type 1. For totally uncorrelated signals, both the spectra of type 1 and type 2 produce the same damage, which is lower up to 5 times with respect to the damage for the spectrum of type 3 for omega r equal to 0.1 and decreasing up to 1.2 by increasing the position ratio. And finally, for partially correlated signals, the greater damage is that for the spectrum of type 2, which is only 1.1 times greater than the damage for the spectrum of type 1. And now let us move to the conclusions. The influence of shape value of the power spectral density matrix components of fatigue damage has been studied by employing the spectral criterion proposed by Carpenter et al. It has been observed that for fully correlated signals, the damage is almost independent of the shape of the power spectral density matrix components. For no proportional loading and totally uncorrelated signals, triangular spectra are more harmful the more the pulsation ratio is lower, and for non-proportional signals and partially correlated signals, the damage is almost independent of the shape of the power spectral density matrix components. Thank you for your kind attention.
Sabrina, questions?